Hello everyone, this is the Science Chef again. In this video, we'll be learning about the kinetic theory of gases. Please go nowhere, I'll be right back after this break. Would you like to watch more of these tutorials? Like this video, subscribe to our channel and turn on your notification bell. Would you also like to watch all our tutorials on chemistry? Check the link in the description. The gas laws help us to predict the behavior of gases, but they do not explain what happens at the molecular level to cause the changes we observe in the bigger world. For example, why does the volume of a gas increase when it is heated? Studies by Louis Boltzmann, James Maxwell, and other scientists show that the physical properties of gases can be explained in terms of motion and individual molecules, and these have been summarized into 5 statements generally known as the kinetic molecular theory of gases, or simply the kinetic theory of gases. The kinetic theory of gases seeks to explain the behavior of gases by looking at the behavior of an ideal gas. In our tutorial on Boyle's law, we learned that an ideal gas is a hypothetical gas which does not exist and is only used to show how gases ought to behave. The first postulation of the theory says that the molecules of gases in a vessel move randomly in straight lines, colliding with one another and with the walls of the vessel. As these molecules collide with the walls of the vessel, they do so with certain forces over small surface areas of the walls. These collisions result in the average force per unit area exerted by each molecule, which is the pressure of the gas. This explains why gases exert pressure on any surface they come in contact with. The second statement says the collisions of the gas molecules are perfectly elastic. In other words, when two gas molecules collide, their individual energies may change, and one may move faster than the other, but their total kinetic energy remains the same, as no energy will be lost according to the law of conservation of linear momentum. This is also why gas molecules bounce off like elastic balls when they collide with the walls of the containing vessel. According to the kinetic theory of gases, the volume occupied by the gas molecules is negligible compared to the volume of the containing vessel. This is because the volume of the gas molecules is so small relative to the distances between them. Since the distances between the gas molecules is relatively large, gases can easily be compressed to occupy less volume. Also, the coercive forces between ideal gas molecules are negligible. This implies that the molecules of a gas neither attract nor repel themselves, and that accounts for their randomness. Also, if we have a mixture of gases, then the pressure exerted by one type of molecule is unaffected by the presence of another gas. Consequently, the total pressure is given by the sum of the individual gas pressures, according to the Dalton's law of partial pressure. Lastly, the temperature of a gas is a measure of its average kinetic energy. This implies that the higher the temperature of the gas, the higher the average kinetic energy of its molecules, and vice versa. Let's look at the deviations of gases from ideal gas laws. The gas laws and the kinetic molecular theory assume that molecules in the gaseous state do not exert any force, either attractive or repulsive, on one another. The other assumption is that the volume of the molecules is negligibly small compared with that of the container. A gas that satisfies these two conditions is said to exhibit the ideal gas behavior. Although we can assume that real gases behave like an ideal gas, we cannot expect them to do so under all conditions. For example, without intermolecular forces, gases would not condense to form liquids. At high pressure and low temperature, the molecules of the gases come closer together and also possess less speed. This makes the volume of the individual molecules less negligible, and the intermolecular forces will be stronger and better felt, and at a point, the gas liquefies. These are contrary to the assumptions of the kinetic theory of gases, and especially the Charles's law, which assumes that an ideal gas never liquefies. So the question is, under what conditions are real gases most likely to exhibit ideal behavior? At very low pressures and high temperatures, real gases tend to behave like ideal gases, because at these conditions, the molecules of the gases acquire very high kinetic energy and move very far apart from one another, with their intermolecular forces of attraction tending towards zero. According to the ideal gas equation, PV equals to nRT. Therefore, for 1 mole of a gas, PV equals to RT, which means the ratio of PV to RT equals 1. If we plot a graph of PV over RT, against P for 1 mole each of an ideal gas, hydrogen and ammonia, we will obtain a horizontal line at 1 for all pressures for the ideal gas. However, hydrogen and ammonia gases show a remarkable deviation from the ideal gas line at high pressures. In our next tutorial, we'll be starting a new series on acids, bases and salts. If you are yet to subscribe to our channel, kindly do so and turn on your notification bell to get notified when the video is published. Until then, stay out of trouble.